Welcome to today's seventh lecture on probability and statistics, and in this lecture we'll study computing probabilities of unions and complements. We know that union is A union B. For two sets A and B is A plus B minus the intersection of the two events A and B subtracted. And the same is true for the probability. The probability of union of two events is the sum of the individual probabilities minus the probability of happening happening together, their joint probability. This probability is also called joint probability. So this probability is also called joint probability, this one. So why do we subtract it? It's an important question. Why do we subtract A intersection B term? This is because we subtract it because it is included in A as well as in B. When we add these two probabilities, A, probability of A, and probability of B, this term, the A intersection B term, is counted twice because it is included in A as well as in B. So in order to get the union, we know that when we studied union in elementary classes, maybe in class 8, 9, 10, we studied that we count the commons of A and B only once. We don't count the commons twice, right? So this is actually the background of removing this term, because adding counts the commons in A and B twice, and we want this to be counted for only once. Therefore, we subtract this probability once so that the commons are counted only once. So that's the reason of subtracting this term. This is very important. Next we'll study mutually exclusive events, the events that are disjoint. For example, if we look at these two events A and B, there is a portion common in between. This means this is this one. This means this gives us the probability of happening these two events together. But if we have events like this, that nothing is common between A and B, that will give us mutually exclusive or disjoint events. For example, if we toss a coin and we have heads or tails, two options, so we'll either get a head or a tail. We cannot have both heads and tails together. We cannot have a head as well as a tail together. So therefore, having a head on a coin or a tail, they are mutually exclusive events. But if we toss two coins, then getting head on both coins are not each. Getting heads on coin number 1 and getting a head on coin number 2, these two events are not mutually exclusive. For example, if we have this coin for which we have two options, head or tail, and we have another coin for which we can have head or tail. So if we define one event to be the head on first coin, and the second event is, for example, a tail on the second coin, so these two events are not mutually exclusive, because if we toss these coins simultaneously or one after another, that doesn't matter. We can have head on coin number 1 and tail on coin number 2. For example, if we toss these coins simultaneously, we can have head on coin number 1 and a tail on coin number 2. Right, so these two events are not mutually exclusive because they can happen together, they can occur together. But if we consider only one coin, coin 1 or coin 2, only one coin, in that case, getting a head and a tail on the same coin isn't possible. We can either have a tail or a head on one coin. So therefore, getting a head and a tail together on a single coin is not possible. Therefore, these two events are mutually exclusive. For point number 1, they are mutually exclusive for point number 2. But if we consider both coins, if we toss both coins simultaneously, these events are not mutually exclusive, because we can have head on one coin and tail on the other coin. So, for mutually exclusive or disjoint events, probability of A intersection B is 0. Intersection, this probability is also called joint probability, and we can also write it as P probability of A, or put a comma here, comma B, probability of AB, read as probability of AB. This is the same as probability of A intersection B. So we can either write B AB or B intersection B. So these are joint probabilities, and they are equal to 0. Joint probability is equal to 0 for disjoint or mutually exclusive events. For mutually exclusive events, the expression A union B, probability of A union B, can also be written as probability of A plus probability of B minus a 0. Why this minus 0? Because this is probability of A intersection B or AB, or joint probability. Since these are mutually exclusive or disjoint events, they cannot occur together. Therefore, this probability is 0. So for mutually exclusive events, the probability of union of A and B is simply the sum of these two probability terms, probability of A plus probability of B. And otherwise, if they are not mutually exclusive, we have this formula. So we have this general formula, which is reduced to only these two terms if we are dealing with two mutually exclusive events A and B. Right. So for a complement, the probability is simple to calculate. We did that in our last lecture. Probability of A's complement is 1 minus the probability of A. Let's understand the same concept. What concept? The concept, this one, and this one. These three equations gives us three different concepts. Let's understand these three concepts with the help of an example, where we have conducted a survey where parents were called on telephone to ask whether they have a kid in college, and if they have a kid in college, then they have to either they have a kid in college or they don't have. They have to tell us that whether the fee is very high, or the fee is right for them, or the fee is too low, it's too little. So on two rows we have parents who have in the first row we have parents who have kid in college. In the second row we have parents who do not have a kid in college. In the first column we have probabilities for both kind of parents who have kid in college or do not have, but they think the fee is too high. So for this column, these two probabilities, they tell us that the probability that the parents think that the fee is quite high, whether they have a kid in college or not. So similarly for this second column, they give us the probabilities of whether they think that the fee charge is correct or right. And the third column tells that the fee charge is too low. So actually this table gives us a set of 6 joint probability terms. It's a joint probability table. What is this? What does this 0.35 mean to us? This is actually the intersection of the two, or the joint of the two. Which two? Child in college and the parents that think that who have child in college, and they think that the fee is too high. They are 0.35. So it's a joint probability table. So probability of A intersection D, or probability of AD joint probability is this 0.35. And This 0.11 is probability of E intersection C. The parents who do not have occurred in college, and they also think that the fee is too little, 0.11. So E intersection C, probability of E intersection C, or probability of EC is 0.11. Right. Next, we are going to study the sum rule on this example. What is the probability of A? What is the event A? The parents would think that the fee is too high, whether they have a kid in college or not. So what should be that A? Of course, the sum of this column, 0.35 plus 0.25. So probability of A can be written as probability of AD plus probability of AE. Probability of A joint with D, with parents who have kid in college and with parents who do not have kid in college. So probability of A is the sum of this column. A's column gives us 0.6. Similarly, probability of D can also be computed using the same sum rule. Probability of D, the parents who have kid in college. So 0.35 is P probability of DA, probability of DB is 0.08, probability of DC is 0.01. So this is the sum of probability of D would be the sum of all these joint probabilities. This, and this. So the sum of the first row will give us the total probability of D. These probabilities obtained by summing a column or by summing a row, we call them as marginal. Use the term marginal. I forgot to write it here, but now I am writing. It's marginal. These are marginal probabilities obtained by adding sums, by adding rows or columns. Marginal probabilities, probability of A. So in a similar way, we can compute probability of B. That would be the sum of these two terms. Probability of C, the sum of these two terms, and of course probability of E, the sum of these three terms found in the second row. Right, and now we are moving towards the end of this lecture. Complements. Probability of D's complement, of course, would be 1 minus probability of D, because we have already studied that in this lecture as well as in the last lecture. The probability of the complements. And finally, probability of union. Probability of A union D. We studied that, the expression for the union of two, the probability of union of two events in this lecture. This is probability of A plus probability of B minus the probability of the intersection or the joint probability. So we apply that. Probability of A union B is probability of A plus probability of D minus probability of their happening together, AD, A intersection D. So putting all these values that we have calculated previously gives us this probability, 0.69. So in this lecture, we have studied how to calculate probabilities of union and complements. In the next lecture, we will study more about probabilities of mutually exclusive and independent events. Thank you.